Hello, thanks for attending this SIMTY 2020 session. My name is Kieran Kunhya from Open Broadcast Systems, and I'm going to be talking about deploying RIST in the real world. So quick sort of introduction. Who are we? What is Open Broadcast Systems? We're a company specializing in software-based encoders and decoders for sports, news, and linear channel contribution. This is a business-to-business thing. We're based in central London, as you can kind of see in the diagram, in the map. You can see Big Ben from my desk. And we build everything in-house, hardware, firmware, software, you name it, it's built in-house. So we have very strong experience in a wide range of technologies. What are the problems RIST is trying to solve? RIST is trying to solve transport over the public internet. And the traditional way that this has been done is using FEC, and I'll go into more detail after this. But the biggest problem is that it can't cope with large burst losses. It's pretty limited interoperability. I'll go into a bit more technical detail afterwards. And the implementation itself is pretty complex. That said, there are some very good proprietary protocols out there for video transport, but they come at quite a high commercial cost. Customers aren't really willing sometimes to pay per gigabyte, for example. Often the protocol itself costs more than the connectivity. So there are a ton of commercial and technical challenges. And I'm sure many of the other RIST forum speakers will go into similar levels of detail into what these are. So let's quickly have a look at some of the technical issues behind forward error correction. So for those who aren't aware, SIMTY 2022-1 FEC is based around rows and columns. So in the diagram, if you lose a packet along the row, that's recovered by the FEC. Likewise with the columns, if a column packet is lost, that's also recovered by the FEC. There are some interesting interoperability issues. Some equipment needs block-aligned FEC and some equipment wants non-block aligned. In particular, the latency tables in the SIMTY spec have been wrong for about 10 years, which also causes a lot of confusion. So those are the real challenges at the moment. So where did we kind of start with transporting video over the public internet? And we've used FEC for a number of years, and I would say broadly speaking, this is good enough to be used within a region, say Europe. In 1.4 of our product, we added something called dual streaming. So this lets us use multiple paths to transport video. So that kind of helped. And then later on, we added our own sort of ARQ based off existing IETF standards, RFC 4585. This is a retransmission protocol. That's very, very simple, and is what RIST has ended up being based on. The big sort of elephant in the room is why did we not incorporate the SRT protocol? And so the SRT protocol was released by Haivision in April of 2017 as an open source project. It's a very complex code base, but to be fair, it's very, very easy to integrate. It's built on a file transfer protocol known as UDT. In my opinion, it has some kind of odd design decisions. It has its own sort of weird input and output timer mechanism. It doesn't really use the PCR. But it did some interesting things at SRT. It drove the market for an understanding that there's a difference between business-to-business video transport protocols and business-to-consumer protocols, often higher latency and with different technical requirements. The spec release that they did was pretty impressive, 89 pages, and went into quite a bit of detail for a very complex protocol, to be fair. I mean, they suffer from one big problem, and that's technical debt. And UDT is really the big technical debt. It's a file transfer protocol. And so for those who aren't aware, SIMTY in particular, technical debt is when you have issues in software that it's easier to take the short-term approach than take a longer approach. And this is a big thing in Silicon Valley. Silicon Valley is obsessed with technical debt. They need to iterate quickly, and iterating quickly is blocked by technical debt. It's pretty difficult to debug SRT issues as well. It's complex to add new features that we want. And so in particular, we needed multi-network support from day one. And that's one of the reasons we kind of looked to RIST. And I'll go into a lot more detail about this shortly. So I mean, our personal viewpoint, SRT is widely supported and it kind of works okay. It's good enough. But it's difficult to add new features. And so SRT will kind of be the prosumer sort of format, RIST for the professionals out there. Kind of analogous to HDMI and SDI. So let's look at some initial RIST deployments. You can do as many tests as you really want with network emulators, etc., but nothing beats reality, nothing beats the real world. And so we rolled out our first beta about a year and a half ago now as a backup on a few sites. There were some customer responses fed back. In particular, we're doing retransmissions on both links. And then gradually changes were deployed to production to the point where I think millions of viewers watch RIST error-corrected content daily and wouldn't know or even care that it's going over an unmanaged public internet transport. And so this map's actually a bit old. I think we've got more now deployments, but there's RIST nearly on every continent, getting there. And I would emphasize for high value content. And so we do it for real. And this is kind of the real crux of this presentation. 24/7 linear channels doing satellite uplink from playout, interactive talking heads, two ways, live events, long-form studio programs. These are often primary paths as well, and a reverse visions for monitoring. So there's a ton of different use cases that we do RIST, often using multiple ISPs for real. And let's look at doing it for real. This is probably the most interesting one out there. This was a video transport from London to New York over 10 months. And it had two ISPs, most importantly, something which other competing protocols can't do, as I mentioned. And throughout this period, each ISP had their own packet loss, outages, etc. But you can see that every single lost packet was recovered with a total of 0 packet loss. And this really shows that RIST is capable of transporting high-value professional content. So operationally, there are also some quite key advantages to RIST. It can be said in the day of Zoom, Skype, etc. You don't really need IP engineers. It's just magic. It works. But this isn't really true. And so one of the big benefits of RIST is just to be able to run TCP dump or Wireshark existing sessions and seeing what's going on. This is really useful. So to be able to see RTP packets, to be able to see RTCP packets, and be able to debug issues here and there. So now what we've done, kind of RIST, done it works. I want to do large-scale content delivery using the RIST protocol. There are encrypted VPNs. Is a way that we've been doing it so far. The new RIST main profile allows other mechanisms to do that, including pre-shared keys and certificates. But from our point of view, we always sort of need a VPN because we're doing control. Again, this could be tunneled over RIST, but from our point of view, it's not as interesting, the main profile, but I can see other applications for it. We're very strong on one-touch provisioning of encoders and decoders. We need to send equipment to sites where people don't even know what the equipment is and have it phone home. And port 443, for example, that will work. But probably the most important thing out there at the moment is the cloud. And one of the big pushes has been to use the cloud for professional broadcasting, but there are a ton of issues. It's relatively straightforward to do your OTT, your web work, your consumer workflows in the cloud. This is kind of a well sort of understood field. But here's a good example of how some end users can do live broadcasts in the cloud. And this is from Google Cloud Next in 2018, a cloud event. Unsurprisingly, wants to use the cloud to produce its content. Unfortunately, this predates RIST, but there's no real reason why RIST couldn't be used in the future. And so they had encoders and decoders at live events locations that fed into the cloud. These then rendered into multi-viewers that were rendered and displayed in the cloud and displayed locally, but rendered in the cloud. Storage was, of course, done in the cloud with Google Drive, and editing was done in the cloud. And in particular, in this sort of post-COVID era where you can't have lots of people in the same place, lots of people are sitting at home, having access to the cloud is really important. And a protocol like RIST makes that happen because the cloud, connectivity into the cloud is inherently lossy. It's there to support lossy IT services. In the end, where are we? We've deployed RIST in dozens of global locations for a wide variety of broadcast services. And RIST today gives us what we need to do that, to transport high-value video in an interoperable fashion across multiple ISPs. It will let us use the cloud in the future, so we can spin up and spin down broadcast services as we need them. And that's really about having the flexibility that we need today.